Okay. So now one of the things that we see here is that you do merge, and merge takes order n time. Okay, merge is needed because some elements. So if I started out with the list 22, 23, 56, 72, and 12, 13, 89, 62, let's say, then I'll try to sort 22, 23, 56, 72, which is already in sorted order, nothing much to do. 12, 13, 89, 62, I'll try to sort it, and if I sort it, it will become 62, 89. I can't just concatenate these two lists because already you have 12 and 13 are smaller than even 22, right? So I have to actually do this merge procedure, and the reason I need to do it is because some elements in front are greater than some elements in the back. But suppose I managed to create two sublists such that everything in front is less than everything in the back, and now if I recursively sort, all I need to do is not a complicated merge but just a plus plus. Okay, and that is the idea in the next sort. Can we ensure that everything in front is smaller than everything in back? So the front portion and the back portion. Yes, we can. Suppose the median value, the value that is sort of in the middle of the list, if you had to think of the list in sorted order and pick the element in the middle, that is the median value, right? Suppose the median value is m, then you can move all values less than or equal to m to front, and all values greater than m to back, and recursively sort front and back, and finally all you need to do is sort front plus plus the singleton list consisting of the median element plus plus. In fact, you don't even need to do that because you're putting the median element also as part of front. So all you need to do is sort front plus plus sort back, where front is all elements from the list such that x is less than or equal to m. Back is all elements such that x comes from the list and x is greater than m, right? So that would be an algorithm, that would be a program, provided you can figure out this median value m. How do you find the median value? One simple way to find the median value is, as I told you the definition, you sort the list and pick the middle element, that is the median element. But if you need to do sort to find median, and then if you use median to do sort, then this is not a good strategy at all, right? Our aim is to sort, so how do you sort and pick the middle element? So what we do in this next sorting algorithm is not to really find the median, but we will pick some element, okay, it doesn't matter. So pick some value in the list, and we will call it the pivot element, okay, it is some value in the list. You split with respect to the pivot element, and usually we will pick the first element as the pivot, this is all, okay. So now sort of empty list is empty list, sort of x followed by x's is sort of front plus this pivot element, that's a singleton list of its own, plus and then you finally have sorted order of the back list. What is pivot? Pivot is just your first element x. What is front? It is all the elements in the tail in x's that are less than or equal to x. Notice that you still have to add the pivot element as part of the final list, because even though here we say less than or equal to, it is all elements less than or equal to x in x's, okay. You have your x that is still left over, and that x should come in the middle, and back is all y from x's such that y is greater than x, okay, and that's it. This is an extremely simple program to write. There is no complicated notion involved at all, okay. All you are saying is that I will hope that the first element in a randomly generated list will be sort of in the middle, so I don't care. So what I do is I will split the list into the first half and the second half, and I will just put the pivot element inside and sort this and sort that. It's already in the sorted order, okay. This is my goal, and it is possibly one of the simplest sorting algorithms to express in Haskell. Might not be so easy in other languages like whatever you have, so other imperative languages, but this is extremely simple to state in Haskell. It's a very elegant algorithm, Okay, and in fact you can write it in one line. You don't even need to have this front, back, etc. Uh, as local definitions. So you could just write sort of empty list is empty list, sort of x colon xs is sort of y from xs such that y is less than or equal to x plus plus singleton x plus plus sort of right. This is almost like the definition of sorted order of a list. The sorted order of a list is if I pick an element, bring all elements less than it to one side, bring all elements greater than that to one side, put this element in the middle, sort this, sort that. That is my sort of the original list. So, and you can just write it, and that's a Haskell program. Of course, this program is a little more sensitive to what pivot you pick. So, if your x turned out to be something that is the smallest element, let us say, then your performance will be bad, as we will see in a minute. So, worst case is when the pivot is maximum or minimum, right? Because if the pivot is maximum, if the pivot is maximum, then your all y in all y such that y comes from x's and y less than or equal to x will be all of x's. Okay, and if the pivot is minimum, then if pivot is minimum, if x is minimum, then all y such that y comes from x's and y greater than x will be equal to x's. Okay, so and the worst case would be if your list is either in ascending order or descending order, because every time you pick a pivot, it will be either the minimum or maximum, and then you will end up. So what will happen? One of your front or back, one of them will be actually empty, and the other will be of length one less than the original list. So you started out with a sorted list, but you end up just spending an enormous amount of time splitting this list and then doing plus plus, etc., etc. Okay, so this is a not the most efficient algorithm. So that is the worst case. Okay, one partition being empty while the other partition being of size n minus 1, and partitioning itself takes time order n, because you have to go through the whole list and pull out everything on one side and pull out everything on the other side. And actually there is a built-in function in import in data.list called partition. Let us just go and check what its type is. We have already imported data.list, so we can actually check the type of partition. Right? You have a predicate a arrow bool, and then you start with a one list, and then you split it into two lists based on the things in the first list are those that satisfy the predicate. The things in the second list are those that do not satisfy the predicate. Let us see if I still have x's. I have this random list x's. So let me just pick an element here. In fact, I will do the following: partition okay, so just a minute. Oh, sorry. It's just a Yeah, so now you see that all positive numbers are put in the first list. This is a long list, so it's a little difficult to follow. So let's try a different list, Y's, which is a random list of length 100, let us say, consisting of elements from minus 200 to plus 200. Okay, this is a random list. Now I can actually do partition less than or equal to 0, let's say, less than 0. Yes, you see that you have two lists here. The first list extends all the way from here to here, right? And as you can see, these are all negative numbers, right? The minus 109, minus 63, minus 190, minus 106, etc. And the second list extends all the way from here to there. And you can see that these are all positive numbers. So this is what partition does. It goes through each element and it, depending on whether that element satisfies the predicate or not, it puts it in the first list or in the second list. Okay, and yeah, partition from right. So partitioning takes time, order n. Okay, so some C of n. In fact, actually, we can write the program for partition. Let's call the predicate P. Partition P of empty list is just empty list comma empty list. Is let FB be, let FB equal partition P of x's in if P of x, then x dot f comma b, else f comma x dot b, right? Depending on whether P is true of x or not, you will either put it before f or after or before b. Okay, so this is partition, and clearly it takes order n time because there are n recursive calls at most, right? Okay, good. And your partition takes that much time, and there is no merging, etc. But your in the worst case, this is the worst case analysis. Yeah, your Tn is T of n minus 1 plus Cn, and if you expand, it will be order n squared. But one's hope is that your whenever you pick a pivot, it's sort of in the middle, and so therefore your time complexity will be more like that of merge sort, while avoiding the complexity of merge. You just do partition, you don't have to do merge, and partition takes order n time, so the same kind of recurrence you can write. Let me just expand it out for you. If it is close to the median element, then you can sort of assume that it is almost like this. Okay, and then this is the same recurrence relation that you had for merge sort, so your Tn will be order n log n. Right, but you cannot make such an assumption. What people have done is actually for quicksort, they have actually figured out the average case complexity. They have done the mathematics to look at the time taken by this quicksort over all inputs and then averaged. Okay, and it turns out to be order n log n. Okay, so you can do this estimate for quicksort, but you can't do such an estimate for all algorithms. Okay, it's a difficult process. Okay, so yeah, so how do you do this? One way to do this is this: assume that the input is a permutation of 1, 2 to n. The actual values are not important. All that is important is what is the relationship, what is the how does each element compare with other elements? Is it less than, equal to, or greater than? That's all that is important. So you might as well think of, if you have a list of length n, you might as well think of it as 1, 2 to n, and you want to consider one way of computing this average case analysis is to assume that your input is a random input in this uh, range. So basically it's a random permutation of 1 to n. Okay, and each permutation is, so yeah, random means random with uniform distribution. So with uniform probability, any of the n factorial permutations are possible as your input. So you will actually take time taken for each permutation across all inputs and divide by n factorial. That is the average case analysis. Okay, and then finally you show that this can be shown to be order n log n. You might have to do some probability calculations, etc. But this is the time complexity of insertion sort. True, it is bad in the worst case, but if I just try it on some random randomly generated list, it might not be too bad. Okay, so now what I'll do is, to end this lecture, I'll go to VS Code again and I shall program quicksort and I'll run it on a few examples and we can compare times. Okay, how quickly it is. Right now I have not enabled various measuring the time, etc. in GHCI. You can check the documentation for GHCI to figure out how to enable these things, where every time you run every time GHCI evaluates an expression, it gives you how much time it took, etc. So, and there is various things like profiling and measuring actual time taken, etc., which I am not going into in this course, but this is part of general programming which you can just pick up. Yeah, so you could do that also, but we have shown that the running time complexity of the time complexity of quicksort is order n log n on average, is order n squared in the worst case, but in practice it might perform well. And the most important thing about quicksort in Haskell is that the program is very, very simple. Okay, that's the nice thing. So let's now program it and see how it performs on a few inputs. Okay, so let's go to the end and we'll say qsort of empty, once again it's of type this is the general type of sort, as we've already mentioned in a lecture, because it doesn't matter that it should be only integers, but it should be the elements should be from any type where the type allows comparison between elements for order. I mean, there is a notion of less than or equal to in that type. Okay, that's all it means. Qsort of empty list is empty list. Qsort of x followed by x's is qsort of front plus plus singleton x plus plus qsort of back, where this time I'll just use the partition function. Partition the list x's based on whether the elements are less than or equal to x or greater than x. Okay, and you are partitioning the list x's, not the list x colon x's, so you have to add the singleton x back again. Yeah, okay. So let's just check how this works. Let me once again pick some random list. Okay, it's actually a truly random list because I have like minus 477, etc., etc. So I can do q sort of yes, and I get actually a sorted list, because you can see that in this list now, yeah, it starts from minus 500, minus 499, etc., etc. It's all minus, and then it becomes plus and goes all the way up. Okay, and this was reasonably quick because it was a random list that I chose. If I had chosen some already sorted list, then it would take a lot of time. Okay, but yeah, so that's basically it. So you can so sometimes it will be hard for you to visually look at this and check if it's sorted or not. So actually you can, one useful thing for you to have is to write a small function called isSorted, which will tell you whether your list is sorted or not. isSorted of empty list is empty list. isSorted of x for singleton list x is isSorted of empty list is true. isSorted of singleton list x is true. isSorted of x followed by y is isSorted is x less than or equal to y, and isSorted not y's but y followed by y's. Yeah, you are checking the first two elements and then you are checking the rest of the list whether it is sorted or not. So now let's go to GHCI and reload this thing, and then we once again have to spawn a new random list and quick sort this. Let's call this y's. Let's just print out y's. This is the sorted order, but you can verify it with a program. isSorted y's, you will need to get true. Okay. Okay, so this is about sorting. In the future lectures, we will look at more concepts and more algorithms and data structures. Okay, thank you.